Okay, great. So thanks, Henrik. Thanks, JJ. It's great to be speaking at QCD Meets Gravity. I'm really amazed. Chris White and I organized the first of these things about 5 years ago now, a little under 5 years ago, I guess, here in Edinburgh. I think it was 40 participants. So I'm amazed to see more than 200 people registered for this. It's fantastic. Anyway, so yeah, I'm going to tell you a little about some work I've been doing recently on another dimension of Kerr. So give you more of an idea. What I mean by that, it's more of some sort of an amplitude / Newman-Janis approach to the effective dynamics of Kerr. So this is work I've been doing with Alfredo Guevara, Ben Maybe, my student who's looking for a postdoc around about now. If anybody's interested in this stuff, you know, Ben, good guy. And there's also with Alex Ocherov and Justin Vines. Okay, so let me begin by reminding you of what this Newman-Janis stuff is. So it's a really remarkable fact, an exact fact about the Kerr black hole solution, the spinning stationary Kerr solution, and also about its friend in electrodynamics, this root Kerr solution. So root Kerr is some solution that is related to Kerr in the double copy. Now, this Newman-Janis thing, it's chiral. So to make it clear, you should use a chiral formulation. So a good thing to do is to pass from the field strength, say in electrodynamics, this is the root Kerr field strength, to this object phi, which I call the Maxwell spinner. So it's just obtained by hitting your field strength with the generators of rotations in the spin representation, one of the spinner representations. Actually, it's very easy to think about in electrodynamics. So this Maxwell spinner is literally E plus IB dot sigma, Pauli sigma matrices with their indices in just the right place. Now, so the Newman-Janis fact is that the Maxwell spinner of root Kerr is obtained from the Maxwell spinner of Coulomb by performing a complex translation. So if you're an observer sitting in a position X, it's as though you've translated the location of the charge in the Coulomb solution through a distance minus IA, right? So if this picture here, if the sort of greenish sheet is our space-time, you've got some observers sitting there at some point X measuring the Maxwell spinner. They'll measure the Maxwell spinner almost a Coulomb, except for the fact that the charge is somehow displaced off your real space-time by some distance A. So this red distance here is a spin. Okay, now you can do exactly the same thing in general relativity. So it's exact. You pass from the Weyl curvature, the conformal curvature, to a Weyl curvature spinner, again, which is some sigma matrices, and the Weyl curvature spinner of the Kerr solution is equal to the Weyl curvature of Schwarzschild, except with this funny shift. So you've kicked your source somehow off the real spacetime in some direction IA. Okay, now, classically, this is very mysterious. We have a partial understanding from scattering amplitudes. So this goes back to these minimally coupled amplitudes introduced a couple of years ago by Arkani, Hamed, Huang, and Huang. So these are massive amplitudes, which have some nice high energy behavior coupling to either photons or gravitons. So I have here the amplitude for a massive particle spin S. Now you can write it in terms of a factor, which is essentially just the amplitude for a scalar particle coupling to a photon, so some sort of a Coulomb type amplitude, times a factor that encapsulates all of the spins of the particle. So this is a spinner bracket here. Now, in a classical application of this amplitude, the photon, so I have in mind electrodynamics here, so the photon has some momentum which is of order h bar essentially, so some small little momentum, very small compared to the big classical momenta of the particles running through, the massive particle running through this diagram here. So so the outgoing momentum, momentum 2, is just basically momentum 1 plus a small little tickle from the photon, right? So in view of that, the spinner bracket simplifies. It takes this form here. Now, little s here is the spin vector, k is the momentum of the photon, and big S is the spin quantum number. Now, if you take S to infinity such that the spin vector, so take big S to infinity such that the spin vector is a fixed spin vector, this thing goes over to an exponential. So I'm just taking this big S to infinity here. A is a length. So A is S over M. So it is the length associated with that angular momentum. Right? Okay, now the amplitudes then just take this form. So there is an exponential factor for this root Kerr, and similarly, there's an exponential factor for Kerr. We can recover things like, if I've got a Kerr source, I can scatter a probe particle off it. This amplitude recovers all of the spin dynamics of the Kerr source that way. So that's sort of an amplitudes-based understanding of why you've got this, this simplicity, the level of the solution. But there's something a little bit funny about this if you think about it from the perspective of scattering amplitudes. Right? And the funny thing is that amplitudes are good for interactions. Amplitudes are things we use just for solutions. We scatter things. We're good with interactions with amplitudes. So if there's a Newman-Janis shift for the solution, and the amplitudes have a Newman-Janis shift, well then you'd think maybe there's a Newman-Janis shift for the interactions too, right? And that's what I want to look at, is can we understand the interactions of a Kerr moving around the place using Newman-Janis sort of ideas. Okay, now, so to do so, what I'm going to do is start from this 3-point amplitude, this root Kerr amplitude, and build an effective action. Now, effective actions are things that we can compute using a matching calculation. So I need some piece of information that I can compute from both my 3-point amplitudes and my effective action. And one thing that I can definitely compute, like I'm an amplitudes guy. I want my amplitude, my 3-point amplitude, to be a fully on-shell thing. So I will compute this thing here. It's actually the Maxwell spinner of a solution described by this scattering amplitude. So this formula derivation will appear hopefully this week in a paper with Ricardo, David, and Matteo. But what it just does is, given a 3-point amplitude, it spits out a Maxwell spinner for you. Now, one thing you need to notice about this amplitude is the d5k here is an integral over massless particle on-shell phase space. And there's a delta function here which forces the photon to have 0 energy. So you're not going to be able to use this formula in Minkowski space, where there is no massless 0 energy on-shell phase space. But it works perfectly fine in 2-2 signature. So I will analytically continue to 2-2, where my 3-point amplitude is a perfectly sensible thing. This phase space is a perfectly reasonable thing to integrate over. I can certainly analytically continue my action there, match it, and then analytically continue back to Minkowski. Okay. So we're going to take an excursion into 2-2 signature for a little while. Okay, now the structure of the effective action will be familiar to many people in the audience. It was the gravitational version, very similar, was developed by folk in this audience, potentially in this audience, I don't know, Raphael, Ira, Michel, Jan, going back to older work by Hansen and Regge. But here's the action I'm going to be looking at. Now, the SPP is the action for a spinning charged point particle. And all of these other operators here are 1 photon operators. I'm just matching to a 3-point amplitude, so I'm only going to have 1 photon. I only want to write 1 F. Now, there's 2 basic structures here, terms with alphas and terms with betas. The reason for that is just parity. Like, I'm going to assume that my system is parity invariant. So then anytime, the thing is, once you've got a spin vector, it's a pseudo vector. So if you've got an odd number of pseudo vectors, then you need to have something else which is pseudo. So in this first term, I've got an odd number of A's. So I'm going to put in an F dual. And in the other term, I've got an even number of A's. So I'll just get away with an F. Very good. Now, one important caveat, which will be important throughout this talk, I'm just putting in the 3-point amplitude. I'm ignoring any higher point amplitudes. So this effective action in principle, of course, has terms with F squareds and F cubes, etc. I'm not going to get those because I'm only going to put in the 3-point amplitude. So I'll systematically neglect higher dimension operators in this talk, and I will from time to time just reorder that basis. Okay, so here's the effective action. Now I'm going to continue into space-time of 2-2 signature. It's very natural to do that in the direction of the spin, right? To do the analytic continuation in the direction of the spin, just because of this plus IA here in the Newman-Janis shift. So if we set Z to minus IZ, and we continue like that, then this just becomes a normal translation. So you don't have to do this, but it's very natural and it has some nice consequences. Okay, so now when I do the analytic continuation, there are some i's, they always come in pairs. So there are some signs. I'm just absorbing those into these alphas and betas, and I'll ignore them. And now I'll start exploiting some of the nice things you have in 2-2 signature. So one thing you have are real self and anti-self dual parts of the field strength tensor. So defined this way. So I can break these, I can rewrite this F star and F, the dual, and just the ordinary field strength in terms of its self dual and anti-self dual parts. So doing that, the sum tidies up a little bit. Instead of being over odd and even numbers, you just have a straightforward sum over n. And again, I've redefined alphas and betas. So, and now I'm going to dump half the terms. They're just the same. It's just you change a plus to a minus. I'll call them with the chiral conjugate. Once you've got half the terms, you get the rest. Okay, and now let's do the matching. Right? So the amplitude has this exponential structure. So it's not too surprising that you find that all of these terms look kind of like an exponential, right? But you see, they're not quite an exponential. They're it's n plus 1 factorial, but n. So you can write that as this quantity here, and e to the a dot d upstairs and then a dot d downstairs. It's a bit weird, right? But on the upstairs, well, maybe e to the a dot d, that's a translation operator. Newman-Janis is some translation thing, kind of makes sense. The inverse derivative downstairs is a bit funny. We can deal with that by introducing an integral, right? And that's what I'll do. So I'll rewrite this thing as an integral. Right? So the effective action has this sort of term. There's your usual term for a charge. These are the interaction terms with the electromagnetic field. And then there's another term. It's an integral over a two-dimensional region, not a one-dimensional region. Right? So there's some sort of world sheet that's appeared. It's just the region that you're integrating over. This is my other dimension of Kerr, by the way. So the meaning of my title is pretty literal. I'm just telling you that Kerr has a second dimension. Now, this world sheet, well, it's a little bit funny, but it has two boundaries. I'm going to give them names, right? So there's the boundary, which I'll call the near boundary at lambda equals 0. You'll see why I'm using these words in a moment. And a far boundary at lambda equals 1. The structure of this effective action then is a little bit weird, but if you grew up as a phenomenologist like me, it's not amazingly strange. There's two kinds of terms. There's a term you integrate over some boundaries, and there's a term that you integrate over the bulk, the interior of the thing. So it's familiar from sort of brain world scenarios. Now here I've also chosen just to write this thing in sort of the prettiest possible form. So there are some dots here. So that means I've potentially just rearrange some hard dimension operators here to make this term look nice. Okay, now if we take this world sheet seriously, some nice things happen. So one of the nice things is that this Newman-Janis shift becomes a very trivial thing. It's just an integration by parts, right? So you see, the point is to compute the field strength of this electromagnetic field. There's some observer here to point x. You do it by integrating Green's functions against sources, right? Now there are two kinds of source. There's a source on this near boundary. That was where the ordinary charge operator is, and then there's the term in this bulk, and you have to integrate over both of these things. So the Maxwell spinner takes this sort of form. There's some derivative. But the point is that you find that there's a total derivative in this lambda direction. So this is the direction parameterized by the spin. So you just integrate by parts, and you find that the bulk cancels against this near boundary and just leaves you with the far boundary. Right? So that's the Newman-Janis shift. It's just integration by parts. Now, when we've got this thing, we can analytically continue back to Minkowski space. None of this stuff goes away, it's still there. You just find that there are i's. So there's an I in the coordinate here that you're integrating over. There's some I that appears in the action. You just take real parts in the end. The F plus now is got an I in it. It's no longer purely real. It was only purely real in the 2-2 context. Again, I'm neglecting some series of higher dimension operators that might be present. But the picture then is this one here. So you have a world sheet, well, we have our space-time, and it's like the world sheet is somehow sticking out of the space-time through some complex direction. So it's sticking out into a complexified version of space-time. And of course, that's where the plus I is coming from in the Newman-Janis shift. Now, Ben is going to talk a bit more about this Minkowski space stuff in his talk in a few minutes. So he'll explain that there is indeed a Newman-Janis shift for the interactions as well, which is one of the nice things that we sort of get out of taking this worldsheet seriously. Okay, so this is QCD meets gravity. Oh, thanks, Henrik. This is QCD meets gravity, so it's time for us to move away from the QCD and move towards gravity. So what about actual Kerr? So the first thing we need to do is embed this, I'll embed this root Kerr solution in a curved background. So, and what you find when you do that is very straightforward, really. The region of integration, this region that this worldsheet is sitting in, becomes curved, and you have to integrate over geodesics generated by the vector A rather than just straight lines generated by the vector A. Other than that, it goes through pretty much unmodified. It's pretty straightforward. And now to get the actual dynamics of Kerr rather than root Kerr, we can see the structure by the double copy, basically. Now, you're using the double copy. You got to remember that it's not electrodynamics that double copies to gravity. It's Yang-Mills theory that double copies to gravity. So rather than writing charges, I should really have color vectors here. So these color vectors and these velocities and spins are contracting then into a 3-index thing, and the field strength tensor in Yang-Mills theory. Now, one thing I can do is swap my U for a momentum. Now you got to bear in mind that momentum here isn't just mass times U. So again, there's some higher dimension operators I'm mucking around with when I do that. The difference is higher order in F. So it's an F squared type effect. But now when we do the double copy, well, you see, there's an obvious candidate. I wanted to, well, one way to think about it is the double copy is obtained by replacing color with kinematics. The color here is that factor Ca. So I'll replace it by kinematics, mass times velocity, some kinematic factor like that. In doing so, I'll want a 3-index object in general relativity to absorb all of these indices. And indeed, there's just such a thing. It's the spin connection. So this is sort of the candidate double copy. It's also what we get by a more genuine calculation. So the effective dynamics of Kerr in this worldsheet form is described by an integral like this. So it's the spin connection, some velocity, some momentum, and some spin. Now, a nice thing happens. So it'll be the last point in the talk, really. A nice thing happens when you take the structure seriously again. So that is that if you expand at this this operator integrated over the worldsheet, so I expand saying powers of the spin, you find that it contains the standard spin kinetic terms. So these are the terms that Raphael and Ira were the first people to write about. It's just contained in this worldsheet structure. But also all of the higher dimension operators that all of these people described are contained in, so all the higher dimension one curvature operators are unified in this particular package. So these are all the leading interactions of Kerr. So again, that's the Newman-Janis shift being sort of baked into the heart of the formalism. You integrate over a worldsheet rather than having a sum of terms in a worldline formalism. Okay, so that's all I wanted to tell you about. So my main mission here was to convince people that this Newman-Janis stuff, if you read about this, people say all sorts of things. Newman-Janis, it's a dirty trick. It doesn't really make sense. Bitter things written in papers about what a terrible thing this Newman-Janis stuff is. What I want to try and convince you is you shouldn't think about it that way. It's simple. It's an insight. We should build it into our formalism and profit from it. Now, if you do that, then it seems that you encounter a complex worldsheet. That seems pretty weird, but on the other hand, maybe we can take advantage of it. Perhaps the symmetries of this thing, if you take this worldsheet really, you believe in it, take it seriously, then perhaps the symmetries of this worldsheet can constrain higher dimension operators that you could add. For example, these would be things that would be relevant to the Compton amplitude, like the 4-point amplitude for a spinning particle. Something I'm very interested in. Now, finally, we find that there's a Newman-Janis shift present for the interactions that you get from this this action. So that's the leading interactions corresponding to the 3-point vertex. Now it's chiral, so a good way to profit from that, to build chirality in is to use the methods of spin or helicity in a classical situation. So that's what Ben is going to discuss in just a few moments. Okay, so that's it from me. But just before I go, I have one announcement to make, which is that, obviously it's fantastic having virtual conferences, but would it be even better perhaps to be, meet all together in the same place again at some point in the future? So I'd like to announce that we have a KITP program approved recently on high precision gravitational waves. So this is, ideas of amplitudes, progress in classical gravity, everything together to move towards high precision gravitational waves. It's in 2022, which is hopefully COVID safe. The application deadline is there. So load up your web browsers, I suppose. Okay, thanks.
All right, thank you, Dónal. That's a beautiful talk. And you're almost perfect on time. We have almost 5 minutes for questions. So let's see if there's any questions. If you have questions, raise them and I will see it in the chat or participant list. So I see a question from Lance. So please go ahead, Lance.
Hey, thanks, Henrik. Thanks for a great talk, Dónal. As you know, when you have a dynamical world sheet, you often get a tower of massive excitations appearing, but not always. If there's enough symmetry, then you can remove them, like going from strings to ambi-twister strings. So I'm guessing you're in that ambi-twister kind of category but do you have an idea of what's going on in that sense?
Yeah, I mean, we're sort of building this world sheet like engineers, at each point of the dynamics or the particle's proper time evolution, we find the straight line that you're integrating over. So one thing we don't really have is a geometric understanding of these sort of questions. The questions you're asking. I mean, obviously this world sheet is very stiff. It doesn't have these massless excitations, but we're not treating it as a sigma model, at least not right now. Like maybe you can treat it as a sigma model. But right now we just observe that there is a structure and that it's equivalent to other effective actions that are out there. But yeah, I mean, I think that's a very important question. I don't have a great answer for it.
All right. Anybody else have a question? I don't see anything at the moment.
I think Giulio Salvatore has a question.
Oh. Okay.
No, it was just clapping, not a...
I'll take it. Yeah.